Hello, this is Dong-Soo from the Applied Superconductivity Lab. Today we will learn about the IC or critical current margin. In this lecture, we will cover the IC margin by starting with three critical parameters for superconductivity: critical current density, critical temperature, and critical magnetic field. This section reminds us of what we have learned in the previous chapters because we are dealing with the critical current. Then we will define two critical currents and compare the critical current margin calculated from the load line critical current and operating point critical current. This slide page is a nomenclature for stability chapters, giving variable definitions and descriptions for each technical term. Before we begin with the critical current margin or IC margin, it is better to review the three critical parameters of a superconductor: critical current density, JC, critical temperature, TC, and critical magnetic field, HC. These three critical parameters have thresholds or critical points to maintain the superconducting state. The critical current density is related to this lecture's topic from these parameters. There are two types of critical current margin: load line margin and operating point margin. First, the load line margin has a load line point where the operating current and critical current values are equal. The graph figure in the lower right has operating current IOP on the x-axis and critical current IC on the y-axis. So, if the operating current and critical current have an equal current value of 164 ampere, this green dot point becomes the load line point. Next, the load line is a straight, solid line from the origin point to the load line point. In this graph, this light green straight line from the origin to the green load line point is the load line. For this setting, the load line margin defines how much operating current a magnet has to go up before it quenches. If the operating current is 130 amperes and the critical current of the load line is 164 amperes, using this equation, the IC margin is 20.7%. Second, the operating point is where the certain operating point corresponds to the critical current. In this case, the operating current is 130 ampere, and the critical current of the operating point is 190 ampere, so the operating point is located at this pink dot point. The operating point margin defines how much disturbance a magnet needs to cause it to quench if the magnet is running at a specific operating current. After plugging into the critical current margin equation, the resultant is 31.6%, with that operating point margin having more current margin. However, it is significant to note that there is a high tendency to use load line margin for actual magnet operation. In this lecture, we reviewed that the critical temperature and magnetic field determine the critical current required for maintaining the superconducting state. Then, we covered two critical current margins calculated with load line critical current and operation point critical current. The graph figure in the previous slide showed that the load line margin is the threshold of operating current before the magnet quenches, and the operating point margin is about the required amount of disturbance that may lead to a magnet quenching. One of the key takeaways from this lecture is that the current operating margin may prevent a decrease in critical current caused by external disturbances or uncertainties that may deteriorate the superconductor's stability.